Welcome to this lecture on multithreading. This will be the first video in the series where we discover how we can write parallel code, which can take full advantage of all of the resources on your CPU. Before we dive into the software side of things, let's first set the scene by taking a quick look at the underlying hardware that makes multithreading possible. Let's first take a look at a simplified diagram of a CPU with only one single CPU core. This core contains several registers to temporarily hold short-term data needed for processing. It also contains several units for execution, such as the control unit or arithmetic logic unit. If you're unfamiliar with this setup, I suggest you watch the von Neumann architecture video, released earlier in this series. At the moment, we're only showing a single CPU core, which is capable of doing one task at a time. This CPU can only really do multiple tasks at the same time by faking it, which means executing some instructions from one task before switching to a different task and executing a few instructions there. This sort of fake parallelism is called concurrency. But in this video, we want to talk about real parallelism, and for that we need to introduce the Multicore CPU. As modern workflows have become more demanding, CPU manufacturers have started offering chips containing multiple CPU cores. These cores are essentially clones which contain their own unique registers and execution units. If a single chip now has two CPU cores, it can theoretically handle two streams of tasks completely independently from one another. In an ideal setting, this means that a 2-core CPU would theoretically have double the performance of a single-core CPU. Unfortunately, doubling the number of cores doesn't always lead to double the performance, as these additional cores will still compete for the same resources, namely cache and memory. If you remember back to previous videos, you'll know that most chips split the cache up into 3 levels: L1, L2, and L3. On these CPUs, each core will usually have its own L1 cache, which it can use for short-term memory. But remember, L1 cache is actually quite small, with L2 and L3 being much bigger. But the caveat is that these levels are actually shared between multiple different cores. And because of the limited capacity, it means that each of these cores will compete for cache space. Additionally, each core will also share access to memory. So not only do these multiple cores have to share the capacity inside main memory, but it also has to share the limited bandwidth connecting the CPU and main memory. As we've discussed in previous videos, memory bandwidth can often be the limiting factor in many types of calculations. This limited bandwidth usually bottlenecks performance improvements when you start introducing multiple cores. Now that we understand the basic model and some of the limitations, let's talk about how we can start to take advantage of these multi-core CPUs to help speed up our code. The easiest way to get started with parallel programming is to look at multithreading. Multithreading is one paradigm that we can use to help write parallel algorithms which take advantage of multiple cores on the CPU. So when we're talking about parallel programming, a thread refers to a context in which instructions can be executed. But what do we actually mean by this? Well, if we have a look at a processor's memory, what we refer to as a thread is really the collection of information that we need to execute some code. So in particular, each thread has its own stack which keeps track of the local variables that are needed throughout execution. And closely associated with the stack is the information that's stored inside the CPU's registers, and most especially the program counter, which keeps track of the next instruction to be executed. The stack, the program counter, and the rest of the CPU's registers are all that's actually needed for a thread to continue execution where it left off, and this is why we call it the execution context. So a thread is just a particular abstraction over some of the concepts that we've learnt about previously on this course. But up until now, we've really been talking about single-threaded applications, so where there's a single stack and just one set of current register values. But with this current model of execution, we're not able to achieve any parallelism. But what's nice about the thread abstraction is that we can just create a whole new thread with its own stack, program counter, and set of registers. What's very convenient about multithreading here is that each of these threads will have access to the entire memory space of the process. So each thread can share the same set of instructions, constant data, and most importantly, access to the same object stored within the heap. So now that we have two different contexts for execution, we can run these at the same time if we have the hardware to do so. So let's say we have two physical CPU cores, we can map all of the tasks from thread 1 to core 1, and all of the tasks from thread 2 to core 2. And that way this single process is able to compute in parallel. This model of parallel programming is quite accessible because each of your threads will have access to all of the data that's stored within your program. So for example, if you're storing an array on the heap, each of your threads is able to access this entire array. As each of our threads are able to read from and write to the same memory, it's actually quite easy to write multi-threaded code. And the code that you write will look fairly similar to the single-threaded code that you're used to writing. Unfortunately, this strength of multi-threading is also its biggest weakness. Since all of your threads can read from and write to the same memory, we need to be very careful about how we synchronize execution to make sure that we're still writing correct algorithms. In this video, we'll discuss some of the issues that come up when you try and write multi-threaded code, and I'll present you with some techniques that you can use to make sure you're writing correct parallel code. And as this is a high performance course, we'll also be benchmarking each of these applications, so you'll have an idea of when to use one solution over another. And so to understand and demonstrate these better, let's dive straight into a Julia REPL. Before we actually launch the Julia REPL, we have to tell Julia how many threads to use. We can do this pretty easily with the --threads argument and specify a number. So here I'm just going to specify 8, which means throughout the lifetime of the Julia process, we'll have access to 8 threads, which can be mapped onto 8 cores on my CPU. Once we've launched Julia this way, we can check the number of threads using the threads.nthreads function. If you don't want to specify the number of threads, you can set an environment variable called Julia num_threads, which will do the same thing. You'll see it's now set to 4. You can also set this value to auto, and this means Julia will automatically choose the number of threads that are available on your system. If you're on Windows and open up Task Manager and go to the Performance section, you can see what type of CPU you're running on your system. In the bottom section over here, you can see that the number of logical processors available on my machine is 32. For now, we won't complicate this video talking about why the CPU has 24 cores and 32 logical processors. Instead, I suggest you read up about simultaneous multithreading or hyperthreading, but I've left a link in the description to an explanation on this topic. For now, we'll just stick to 8 threads. So let's have a look at how we can parallelize a simple function. Now I'll assume that the inputs to this function are 2 matrices, A and B. On the first line we calculate A times B, which is quite an expensive operation. And on the second line we calculate the exponential of the square matrix B. This is also quite an expensive operation. And finally we calculate the multiplication between C and D. One thing to notice in this calculation is that the calculation of C and the calculation of D are independent from one another. And if you remember from the last video, this means that we can do these 2 operations in parallel. So now I'll paste in a function which performs the same operations but in parallel using multithreading. We can use the very convenient macro @spawn from the threads standard library. What this will do is take the expression on the right hand side and wrap it in a task. And a reference to this task is what's returned from the overall expression. But @spawn not only creates the task, but it also passes this task to a scheduler, and what the scheduler will do is find an available thread to run that task on. But this operation happens almost immediately, because all you're doing is wrapping it up in a lightweight task and sending it off to be scheduled for execution. It means that this task isn't actually done by the current thread. Instead, the current thread that executes this function will move on to the next operation, which is calculating the exponential of B. A times B will be calculated at the same time as D by separate threads. But since the final operation, C times D, needs to wait until C and D are both finished before executing, we have to add in a command which blocks execution until both tasks are finished. By default, this line won't get executed until D has been calculated, and so we know this task will have completed by the time we reach this line. However, this thread doesn't know whether the previous operation has been completed, and so we need to tell this thread to explicitly wait until the task to calculate C has been completed first. In Julia, we do this with the fetch command, which not only waits for that task to finish executing, but it also returns the result of the expression in the thread body, in this case the result of A times B, and this line will store the result in the variable C. On the final line, we can just continue execution as normal on the current thread. Now let's create some random matrices and time both of these functions. You can see that parallelizing this function led to a very modest speedup. In the first example, the minimum time took around 160 milliseconds, but in the parallel example, this took around 140 milliseconds, just because of the specific function that we tried to parallelize. Let's look at a slightly different example where parallelizing makes a lot more sense. Let's take the map example that we visited in the last video, where we were trying to evaluate this complicated function f for a bunch of different x values, so we could plot this function as a curve. Now I'll just write a very simple function which uses a for loop to evaluate the function f at a few different values of x. In this very simple function, we just take in 2 vectors, y and x, and what we do is we just fill up the vector y with the results of f applied to each element of x. And so this operation is effectively just a mapping operation, but our output here is pre-allocated. When this runs, by default, it will run only using a single thread, and so at most you'll only be using 1 CPU core to actually execute this function. But what you'll notice is that each operation within the for loop can be parallelized, because all of the operations are independent. Parallelizing this loop in Julia is actually extremely simple. What we can do is just use a macro, again from the threads standard library. This macro is the @threads macro. and this is used exclusively before for loops. And what it will do is spawn tasks to calculate each part of the inner loop body in parallel. So let's time both of these functions and have a look at the difference in their performance. For this, we'll be calculating the function f 10 million times. So now with the benchmark results, you can see that the threaded version is actually a lot faster than the unthreaded version, which comes with no surprise. What you might be a bit surprised to realize is that the @thread macro will now allocate in your code. If you remember back to a previous video, you want to try and avoid these allocations if possible, but in this case the extra allocations are worth the cost because the average execution time is so much lower than before. In this case, our threaded version was around 6.4 times faster, just by adding the @threads macro before our for loop. Now this wasn't the perfect speedup that we were expecting of 8, but often when you're doing parallel programming, it's quite hard to achieve this maximum speedup. Later on in this video, we'll talk about how we can get much closer to the maximum speedup, and some reasons for why you might not actually reach the maximum speedup that you're expecting. So now let's look at a more complicated operation, which runs into a few issues when you try and parallelize it using the @threads macro. To keep things as simple as possible, let's use the example that we introduced in the last video, the Monte-Carlo estimation for pi. This Monte-Carlo simulation works by throwing a bunch of darts at a dartboard and using where those darts land to try and estimate a value for pi. So here is the function pi_estimate, which performs this Monte-Carlo simulation just using a for loop. And so all of the darts here will be calculated sequentially. Our goal for this video is to write a multi-threaded version of this function. So this function throws each one of these darts one at a time and adds the number of hits inside a local variable. And this count is then used to estimate pi. You notice that this estimate for pi gets more accurate the more darts that you throw. And in principle, you could throw each one of these darts in parallel. And so this is an ideal candidate for speeding up your code using multithreading. So let's say now that we'll use another version of the function with the @threads macro. In order to keep the code a little bit cleaner, I'll just import the base.threads library, and this will import the @threads macros, so we don't need to specify that we're using the threads package. So this change seems simple enough, but let's see what happens when we actually run our function. Now we're actually getting an incorrect result, and it's much lower than the expected value that we want to see. Even if we increase the number of darts thrown, you'll see that this estimate doesn't get any better. And so you might be wondering, what's actually causing this error? Well, the culprit is this operation that keeps track of the total counts. While this operation seems like it's a single line, it's actually broken down into 4 different instructions. In the first step of the operation, we have to load the value of hits from memory into a CPU. And in the second step, we have to load the value of the isHit result. And if you remember back to the von Neumann architecture video, loading a value into the CPU or reading a value from memory involves actually copying the value from memory into the CPU's registers. Once these values are actually copied into the CPU, they can be added together using the CPU's ALU. This result then has to get written back into memory. The result is then stored in the memory location associated with the hits variable. Now this sequence of operations is completely fine when you're using a single CPU core, but let's imagine what happens when you're using 2 CPU cores. Let's say 2 darts are thrown at the same time, and so our 2 CPU cores calculate isHit roughly around the same time. And let's say that they both load the hits variable from memory at the same time. If we're at the start of the execution of our function, this means that they'll load the value of 0 into the CPU's registers. CPU1 calculates isHit is equal to 1, and so it tries to add 1 to the hits variable. And this result is stored back inside of memory. However, at the same time, the second core was still executing, but now it has an outdated result for the hits variable, and the result inside its registers are still 0. So once it's finished its calculation and tries to add 1 to the result, it will overwrite the hits variable with the value 1 inside of memory. This means that the isHit count from the first core has now been overwritten and essentially lost. And this is one of the main problems that comes up when you try and multi-thread your code. You run into what's known as a race condition. So race conditions happen if 2 or more threads are competing for access to the same block of memory. Unfortunately, race conditions often don't cause a program to crash, but can just produce the wrong results, and so they can be quite hard to catch. The typical examples of race conditions that you see are when you're mutating the same block of memory, either inside an array or a particular variable. Race conditions can also occur when you're trying to append to an array or write to an output result, because when you move to a multi-threading model, the order of execution is not actually guaranteed, because the tasks are assigned to threads based on a scheduler. You might also run into race conditions when you're dealing with random number generators. and that's because most random number generators are actually pseudo-random number generators. And this means that they rely on a global state which is mutated every time a new random number is generated. This means that by default, random number generators can have race conditions. However, languages like Julia will assign a different random number generator state to each thread to make sure that there are no race conditions between them. So we would call the random number generator in Julia thread safe because the designers have added in this mitigation to avoid the race condition. Functions that are thread safe not only avoid race conditions, but they also avoid some other unexpected results that might happen when you run the function from multiple threads at the same time. Unfortunately, what you notice is a lot of algorithms will want to read from and write to the same block of memory at the same time. So what can we actually do to try and avoid these race conditions while still being able to speed up our code? Well, fortunately, you have access to quite a few different options that you can use to try and mitigate these race conditions. The first solution to this problem I want to talk about is atomics. Now, the word atomic comes from the Greek word which means indivisible. So atomic operations are operations that can't be split up into smaller substages. If you use atomic operations, this means that they can be done in a thread-safe manner to essentially eliminate the race condition. So let's look at a simple example of a function which just sums up all of the numbers inside an array. The implementation on the left has a race condition because each of the threads is trying to read from and write to the s variable at the same time. And as we know, the plus equals operation is actually 4 operations in disguise. And these 4 instructions can be executed at different times by different CPUs, which leads to race conditions. But what we can do instead is say that s should be an atomic variable. Marking s as being atomic means that the compiler will produce instructions which interact with the memory in an atomic fashion, ensuring thread safety. We also have to make sure that anytime we use this atomic variable s, we're using the right functions. So instead of the plus equals function, we now have to use the atomic add function. And finally, in order to convert this atomic value back into its raw integer value, we have to use the open and close square bracket syntax. And this simply just reads from the memory that the atomic points to. And so this kind of syntax can help eliminate the race condition that we saw in our Monte-Carlo example. So let's quickly dive back into VS Code and see if we can fix our implementation using atomic operations. So the first thing that we have to do to edit our function is to assign this to be atomic. And what this syntax will do is create a reference to a piece of memory that should be accessed atomically. And we're also specifying the type of this variable to be an integer. Now, instead of using this plus equals command, we want to use the atomic add function instead. Unfortunately, the atomic add command is not defined for the addition of an atomic integer with a Boolean value. And so what we'll do is explicitly convert the Boolean into an integer before we call our function. Now, this function isn't quite complete because we still need to read the atomic variable on the final line in our function. And in order to do that, we can just use the indexing syntax. So now let's execute our function again and see if we get a more accurate value for pi. And as you can see, this is much closer to the true value than our previous implementation. And that's because we've now fixed the race condition. Unfortunately, fixing this race condition didn't come for free. Let's benchmark our 2 implementations to see the speed difference between them. And so unfortunately, our implementation is actually now a lot slower than before. And so it's clear that there's some significant overhead when you're trying to use these atomic operations. Our implementation here was a lot slower than our serial version because we forced the threads to have some amount of communication and synchronization between them to ensure that each thread is dealing with this memory atomically. And this is one general rule in parallel programming. The more communication and synchronization that you have between your various workers, the higher your overhead in parallelizing your algorithm. And this additional overhead can seriously impact the performance of your algorithms to the point where parallelization seems like it's not even worth it. Later on in this video, I'll show you an implementation which uses atomics only sparingly, and this helps vastly improve the performance of this function. But for now, let's summarize the advantages and disadvantages of using atomics. The first advantage is that atomics have intrinsic support in most modern hardware, and so the instructions that we used actually get compiled down into specific hardware instructions for doing these atomic operations. Secondly, and I guess most importantly, atomics will actually help fix your race conditions, which, if you use them correctly, guarantees thread safety. The main disadvantage for this is that atomic operations are actually much slower than their non-atomic counterparts, and so you have to be kind of tactical with how you use them. The main reason that you'll actually use atomic operations is so that you multi-thread your code, and the only reason to multithread your code is to try and improve performance. And so you've got to be careful that you don't actually end up hurting your performance by using the atomic operations. The other main disadvantage is that atomics are only really supported for some data types. And if you need to fix a race condition where you're accessing a more complex data type, for example an array, you might want to use other methods that are available to synchronize operations between multiple threads. So now let's take a look at what other options you have when you're trying to synchronize your code and fix race conditions. Another object that you can use to help synchronize execution between threads is a mutex. And this is one of the most common ways of dealing with race conditions in your code. And the way that I like to introduce mutexes is to use a metaphor. In particular, I want you to think of somewhere with a shared resource. So for example, a room that you can book at your local library. You want this room to only really be used by one person at a time. If someone comes along and tries to use this room, they need a key to unlock the door. And an important point here is there's only one key for this room. Once someone acquires the key for this room, they can unlock the door and enter to use the resources. Once they've entered, they take the key with them and the door closes. If someone else comes along and tries to use the room, they'll have to wait outside until the first person is done using that resource. And that's because this room is locked while it's in use by someone else. No matter how many people are waiting for this resource, no one can come in until the lock is released by the person inside. When the person using the room has finished, they can unlock the door and leave, and the door locks automatically once they've left the room. Now the room is free and the key is outside, the next person can unlock the door, enter the room, and start using the resources. The door behind them will lock, making everyone else wait for the resource to be free. This sort of metaphor describes a process of mutual exclusion, and that's where the name for the mutex operation comes from. So now when you hear people talk about mutexes, just know that they're talking about a way to lock up resources so that only one thing can use those resources at any one time. So let's look at how mutexes are implemented in Julia. If you want to use a mutex, I recommend using the class reentrantLock. If you're going to apply it to this multi-threaded code, which adds up all of the numbers in an inputted list, you would first have to create the lock as a standalone variable before you want to use it. Since we want to protect the line s plus equals n from any race conditions, we want to use the lock function. This function will take two arguments. The first will be the function that uses the resources that we want to protect. In this case, the first argument is provided by the doEnd syntax, which is a special syntax in Julia to declare an anonymous function and pass it into the first argument of a function call. The second argument is the lock itself. Now you don't have to use this syntax, and you can instead use the lock and unlock functions, but this means you have to make sure that every lock is paired off with an unlock. If you don't correctly pair up lock and unlock statements manually, you might introduce a deadlock into your code. This is where a thread hangs because it's waiting for a lock that will never be released, and ultimately your program will never finish executing. So let's talk about what actually happens when this block of code is executed. The first thing that happens is the thread that's executing this code will attempt to acquire the mutex, which means it waits for the resource to be free. If another thread is currently using that resource, the current thread will just wait until this resource is free. When the mutex is acquired, the current thread will start executing the inner body. And this inner body is specified by the do syntax. As the thread executes the inner function body, we can be sure that only that thread has access to those resources. Once that thread has finished using those resources, it will then relinquish its control over the mutex so that the mutex can be acquired by other threads. So as this is fairly simple to use, let's see how we can apply this to our Monte-Carlo simulation. So let's try and implement the pi-estimate function using multithreading, but using mutexes to eliminate the race condition. So in this case, we're going to create our mutex using the reentrantLock class, and then here is where we have our race condition. So what we can do is use the lock function to try and acquire the lock for our mutex here, and then use this do syntax so that we force this line of code to be executed serially instead of in parallel, which will eliminate the race condition. So now if we use this function, the race condition has been eliminated and we get a sensible estimate for pi. So when we tried to benchmark our mutexes function, we see that it's actually a lot slower than our original implementation. In fact, using the mutexes here was around 200 times slower than our original implementation. So if you are going to use mutexes, make sure that it only takes up a small proportion of your overall runtime, because mutexes essentially force a line of code to be executed serially, which essentially eliminates any benefits that you will get from multithreading. And so you would have to use it sparingly throughout your code to minimize the synchronization between threads and maximize the performance gain by using multiple cores. For the sake of completeness, when you're talking about mutexes, you also have to mention semaphores. And semaphores are just an extension of mutexes. Thankfully, to describe semaphores, we can just extend our previous metaphor that we used for our mutexes. Now instead of one room, imagine that we have several rooms available. So in this example, for each room we have, one person can use those resources at any one time. Once all of the resources are used up, anyone else who wants to come in and use those resources, they have to wait until one of the rooms is free. So for example, if someone leaves, the next person is then free to use that resource. So let's go back to our Monte-Carlo example and see how you can implement this algorithm using a semaphore instead of a mutex. So we'll start with our base implementation, but we'll introduce a shared pool of hit counters. The easiest way to create a semaphore is by using the channel struct. Now channels are not exactly semaphores, but they are conceptually similar enough that we can use it in this instance. A channel is just a buffer that you can use in a thread-safe manner, and you can specify the size of the buffer when you construct the channel, which in our case will specify the number of resources that we want to share. But in this case, I want a resource for each separate thread that is available on my system. But first of all, we need to actually initialize all of these resources. So what we can do is add a bunch of counters into this shared resource pool. And we do this using the put function, which provides a thread-safe way of adding items into a channel. So within the loop body, we want to use one of these counters for each one of our threads. And so we can use the take command to take out one of these counters from our hit pool. And when we take out this counter, it's done in a thread-safe way, so that no other threads can access this resource while we're using it. We can then use this variable like normal, and then put it back inside the hit pool. What's important here is that once the hit pool is empty, any new threads that run this take command will wait until one of these resources is put back inside your channel. Once we finish executing our for loop, our hit pool will be full of partial counts, and so we need to add some code to add all of these partial counts together into a single total count. And we can do this pretty easily just by taking all of the elements out of the channel and summing them together. So this implementation is a bit contorted to try and fit our example, and you wouldn't really use a channel to solve this type of problem. The reason why the channel isn't very appropriate here is that the overhead for using this channel is quite large compared to the computation that we're doing per thread. In general, if we were doing a computation that takes up a lot more time, for example, large matrix multiplications, it might make sense to use a channel to create a pool of memory buffers to store the intermediate results of your calculation. For completeness sake, let's actually see whether this function returns a sensible estimate for pi. And as you can see, all of these results average around the true estimate for pi, and so we've likely got rid of the race condition. Now if we benchmark this function, you can see that we have twice the performance of our mutex example, because in this example we just had a single resource that was shared between all of our threads, whereas in the semaphore example we had an entire pool of resources that could be shared throughout all of our threads. Unfortunately, this is still around 100 times slower than our serial implementation, and so here it shows that you need to be very careful when you're using mutexes or semaphores, because you can dramatically decrease the performance of your code. So let's quickly compare the differences between mutexes and semaphores. As we said many times, a mutex provides mutual exclusion, which means that only one worker can access a resource or a group of resources at any one time. This is usually implemented as a type of lock. A semaphore is a generalization of the mutex. But whenever you hear about semaphores, I want you to think of a pool of resources where the resources can only be used by one worker or thread at any one time. What's important about both of these mechanisms is that it's up to the programmer to be able to release the resources a thread is using once they are finished using that resource. And because of the semantics of mutexes and semaphores, you might run into a situation where threads are waiting for resources that will never be released by other threads. And this can cause a deadlock in your code and cause your whole program to hang. So now that we've covered some of the more involved ways that you can try and mitigate race conditions, let's look at something a little bit more basic. So the whole problem with the race conditions in the first place is that we're accessing the same piece of memory using multiple threads. So we can actually just remove the race condition entirely by making sure each thread only accesses an isolated region of memory reserved for that thread. So in our original implementation, our race condition comes from the fact we're using one location in memory. But similar to the channel example, we can create several locations in memory for each thread on our system so that each thread only writes into its own portion of memory. And these will be like partial counts for each thread. An easy way to create room for several integers is to just create an array, where the number of elements is equal to the number of threads that we have available on our system. Once we have the array, we can write into the portion of memory associated with each thread by using its thread ID, which is accessible by the threads.threadID function. At the end of the function, we have to make sure to add up all of these partial counts at the end when we're returning our result. So now let's quickly run this code to make sure it's giving us a sensible result. And thankfully, this implementation is correct. So now let's run the benchmark for this function to see how it compares with our original implementation. And as you can see here, we can finally see some form of speedup. And this speedup is actually pretty good. It's around 15 times speedup when we're using 16 threads. And so this really is an easy way to help speed up your code. Unfortunately, in this implementation, we were forced into making a heap allocation to create an array to store our intermediate counts. But what we can do is actually avoid the heap altogether by slightly modifying our algorithm. So instead of relying on the threads macro to partition our code into multiple separate tasks, what we can do is manually partition our algorithm into different sections and assign each section to one thread that is available. Within each of these partitions, we can perform a local reduction just using a variable that can be allocated on the stack. Once we have these local reductions, we can perform a final reduction into a single variable by synchronizing the results between the threads. And for this final synchronization, we can use one of the methods we discussed earlier, such as the atomic operation. For this implementation, I'm just going to use the atomic variables from before, and we'll use this atomic to keep track of the total count for the final reduction of each of the blocks. And next we need to figure out our chunk size by dividing the number of darts we need to throw by the number of threads that we have available to throw them. I'm using this function CLD, which stands for ceiling divide, and it makes sure that we throw at least n darts in our estimation. Now we want to transform our implementation to a doubly nested for loop instead, with the outer loop being over the number of workers. So next we want a hits counter that's local to each of the threads, but I want to use the name hits, so I'll rename the atomic variable to total hits instead. And finally we can add up all of the local hits counters into the shared total hits atomic variable, and for this we use the atomic add function that we saw earlier in this video. On the last line of the function, we have to make sure that we're extracting a normal integer from the total hits atomic variable. And just as a final sanity check, I've run this function to make sure that we get a sensible estimate for pi. But now let's benchmark this function to see whether the performance has improved. And this implementation is our fastest yet, but it's not that much faster than just using the @threads macro. What's been interesting about rerunning this course is that the performance difference between these two implementations has actually shrunk over time. And in older versions of Julia, the performance difference was much greater. And so now I'll open up Julia 1.6 and rerun these benchmarks so we can see the difference in performance between these two implementations. So as you can see, in previous versions of Julia, the @threads macro actually performed quite poorly, achieving a speed that was actually worse than the serial implementation, at just under 50 milliseconds, whereas the chunked implementation was around 10 times faster, reaching just over 4 milliseconds. What you can see in the newer versions of Julia is that both of these implementations have had their performance massively improved. And hopefully this example shows you that it's worth upgrading to newer versions of Julia because you might get access to performance improvements behind the scenes that might improve the performance of your existing code. So far throughout this video we've been benchmarking all of our implementations based off of only one input size. To better understand the performance characteristics involved, let's look at the benchmarks across a range of input values. As per usual, I'll use a plot that compares all of our benchmarks to our serial implementation which just used a simple for loop. And one thing to keep in mind when looking at this graph is it's plotted in a log-log format. The center dash line at 1 represents our serial implementation, and the grey line towards the top represents the maximum speedup of 16 that we can hope to achieve, given that I've set Julia to use 16 cores. So our first parallel implementation used atomics, and as we saw from our benchmarks, the performance was actually much worse than our serial version. And that's because this simple example didn't have a large enough workload to give each thread before we forced synchronization between the threads using atomics. In fact, this implementation was at best around 3 times slower even though we were using 16 cores. And this is why you should think carefully about how you synchronize execution between your threads, and which problems you apply parallelization to, because you might not see any performance improvements without significantly changing your algorithm. Our next two implementations were based on the mutex and the semaphore, and in particular the Julia implementation of the channel which represented our semaphore. These two synchronization techniques can be quite useful, but it really depends on the problem that you're using them for. In this case, using these type of synchronization techniques actually led to around 100 times worse performance than just using a single core. After these 3 examples, we finally saw an implementation that gave us a performance improvement. And here we just used the @threads macro and assigned a different memory region for each thread, and so we didn't have to deal with any race conditions. But this curve still tells an interesting story. What you'll notice is that for large input sizes, we were able to achieve the maximum speedup possible of around 16 times. If we're to look at the low end, where we're only asking to produce a few hundred points, you'll see that our implementation is still 50 times slower than our for loop. And this dichotomy is very common to see when you're trying to parallelize your code. You need to run benchmarks to make sure you're on the side of the curve that actually gives you a performance improvement. If your problems are actually quite small, you might not actually benefit from parallelizing your code at all, and it might be worth just using the serial implementation. You'll notice here that we had to generate more than around 10,000 points to actually see any performance improvements by using multiple threads. One interesting comparison is comparing this threads macro to the threads-x package that we saw in the last video. In this case, we can see that our custom implementation actually beat out the threads-x package across the entire range of input sizes that we benchmarked. For smaller input sizes, threads-x was around 6 times slower than our custom implementation, but overall the threads-x package is actually quite convenient and can let you parallelize your code quite effectively without risking running into any race conditions, and so I'd still suggest checking it out in case you want a quick and easy way to speed up your code. Finally, we did our chunked implementation, and you'll notice that this had around about the same performance as our threads implementation, but you'll only see performance parity between the threads and the threads chunked implementation on recent versions of Julia. On older versions of Julia, the threads implementation is actually much worse for these smaller types of problems, and you might want to keep this custom chunking approach in mind if you run into a scenario where you're not able to achieve the maximum speedup just using the simplest threads approach. So hopefully now you've seen some approaches that you can use to help effectively multi-thread your code. Unfortunately, this video is only an introductory video on the topic, and there's actually a lot more interesting things you can learn about multi-threading. But for the sake of brevity and to wrap up, I'll just list a few considerations you need to make when you're designing multi-threaded code. The first main consideration is about garbage collection. And while we talked about garbage collection and its implications on performance earlier on in this series, it should be stressed that garbage collection has a much greater impact on multi-threaded code. And that's because when the garbage collector is triggered, it will pause execution on all of your threads. And what makes this worse is that if all of your threads are allocating memory, then the garbage collector will be triggered more frequently, and you'll end up experiencing incredibly poor performance. So if you're thinking about trying to parallelize some portion of your code that has a lot of allocations, you should first try and remove these allocations before you begin parallelizing, because it might severely impact the effectiveness of your parallelization. The second consideration is that you can't just use as many threads as you want. The number of threads you choose has to be related to the CPU that you're using. If you allocate more threads than are available on your CPU, the CPU will try and execute all of your threads in parallel anyway, and will end up just context switching between multiple threads, and context switching is quite bad for performance, and so generally you want to avoid this in a high performance setting. I mention this because it might come up in subtle ways. For example, if you're using libraries like BLAS, which is the basic linear algebra subsystem, these libraries are already designed to be multi-threaded, and this means if you're using multi-threading to call this code, you might be nesting the number of threads that are being used. And so if each of your threads is running linear algebra operations at the same time, and these linear algebra operations are themselves using multiple threads, then you might end up oversubscribing your CPU and massively degrading the performance of your system. Fortunately, this is quite easy to fix, and in Julia you can just set the linear algebra module to just use a single thread, which can usually help alleviate some of these oversubscription problems. The final point I want to mention is that most problems are actually memory-bound operations, and this means that it doesn't matter how many extra cores you add into your system, if you're not increasing the memory bandwidth or the capacity, then you won't actually see any performance improvements by adding multiple cores. And with those considerations in mind, I suggest you try and look at the applications that you're currently developing and try and see which parts might benefit from multi-threading and to give it a go. And that's where I'll end things for this video. In the next video, we'll be talking about multiprocessing, which is a parallel programming paradigm which allows you to scale up the resources of multiple computers to work towards a single goal.